The next big challenge that we have in fluid mechanics is in trying to apply the kind of equations that we've been talking about so far to what we'll call a control volume, or in other words, a large region of space. And we've seen one hint or example of this when we thought about a jet exiting from an orifice. We saw that we could apply the Bernoulli equation, for example, if we have a wall here and we had a high pressure here. We saw that we could apply the Bernoulli equation to think about the idea of straight streamlines coming out and calculate the velocity at which the fluid comes out of this jet. However, we also saw in pictures that very rapidly the jet becomes unstable, becomes much more complicated, and that viscous effects become important here. And we don't really know at the moment how to take into account of those. But we could certainly see that there was maybe a possibility of saying, let's not worry about what's going on inside this. Let's draw a boundary around it and just ask what's happening at the boundary between this. And so this idea of a bounding surface is frequently what we'll call a control surface. And what it bounds, of course, inside it is what we'll call a control volume. And this approach allows us to take in an integral way or in an average way some measure of what's going on inside a very complicated flow in terms of thinking about what comes into the system and what goes out of the system. And you've probably seen very similar ideas, for example, in undergraduate classes in thermodynamics, where we might have a control volume like this where we're supplying heat into it, we're taking shaft work out of it, and we're trying to understand everything that crosses the surface. The reason we have to do this is because we need to write down a conservation equation for what's going on. And the challenge is, so far in mechanics, what we typically know is we know how to apply conservation equations to a little point mass, such as something like this. So our point mass here might have a density, which is a function of spatial position. So this might be at a position x. And our point mass might be moving through it, and it might have a density there. And so we might know how to apply equations that conserve either mass or momentum or energy on our little point mass like this. So, for example, we might write down that a statement of conservation of mass might say something about the time derivative following a material element. So this is our idea of a material derivative. And so we might write down that the time rate of change of mass it can be expressed in terms of this, and we've already derived a result from that. And essentially we've said that there is no creation or destruction of mass following that material element. Of course, we may also be interested in more complicated conservation equations. So, for example, we might be interested in thinking about a conservation equation for the time rate of change of momentum of our little material mass. So it's rho times the volume times the velocity. And the time rate of change of that, we know how to apply, is equal to the sum of the forces that are acting on our mass, m. So that's a conservation equation that we know. What we need to do is we need to take that idea that's applied on a point mass and turn it into something that we can use on a finite volume of material. And so we're going to have to integrate over that. And that means we're going to have to take very, very careful account of what's happening when we're dealing with different surfaces. And to do this, the way we're going to convert this is we're going to use something called the Reynolds transport theorem. So this is not a conservation equation on its own. It's a way of allowing us to take things and go from point mass and the idea of conservation principles and convert it into something that we can apply to a finite volume. So another way of thinking about this is that essentially this is going to be a mechanism to allow us to generalize the idea of converting between Lagrangian descriptions and an Eulerian description. And we've already seen one way of doing that when we think about just acceleration. So we've already seen, for example, that we can think about if we're interested in the acceleration of an object, we know that in a Lagrangian system, this is nothing but the second derivative of the spatial position by d time, where this function is following a material element. This was the idea that we might specify the position of a material element as a function of time, knowing where it is at an initial time. And in the Eulerian sense, we can convert that into a material derivative, which recognizes that there were two ways of changing acceleration, one by changes in time and one by changes in space. And so we should expect the material derivative to show up intensively, just as we've shown here. So the final thing that we need in terms of a notation is to recognize that we're going to have to think about what goes into the argument of these functions. And we can already see an example of what goes into the argument of these functions here. You can see that it's a product of terms, and so we're frequently going to end up with products of terms. And this leads to ideas of things that you might have seen in thermodynamics already, in terms of the idea of the difference between an extensive variable which depends on the mass of the system, and an intensive variable which we can express on a per unit mass basis. And typically what we'll find is that in general we use a capital letter to indicate an extensive variable. So generically I'm going to call our extensive variable f, and we'll frequently use that. And our intensive variable, or the amount per unit mass, we'll typically write as a small or a lowercase variable like this. So we might make a little table of some quantities that we might have seen in the past. The simplest one that we might think about is we might think about mass. The extensive quantity is indeed nothing but the mass of our object, or the mass of the system. And so the intensive quantity is the mass per unit mass, which is just 1. Another common one when we think about momentum, we might think about linear momentum. So for momentum, our extensive quantity is mv. The amount of mass per unit volume is indeed then just v. So another way of thinking about velocity is it's the mass per unit, the momentum per unit mass. However, in fluid mechanics, frequently the way we're interested in things is we're also interested in the amount of something per unit volume. And so we need a way of expressing that. And that's not the same as per unit mass, because our density may actually be changing as well. And so we're going to, if we already have a capital F and we have a lowercase f, we're going to use the Greek variable phi to indicate that. And so phi is nothing but the amount per unit volume. And the way to understand the conversion between these is to recognize that the extensive quantity is nothing but the integral of phi dv over our volume. So we'll always integrate a volume integral as this, and we'll use a bar through it to recognize the difference between volume and a velocity, because that can be confusing. And then we'll recognize that that's nothing but the integral of the amount of quantity per unit mass multiplied by the differential mass. And so when we write the quantity like this, we can relate the intensive quantity, the quantity per unit volume, and the extensive quantity. A final example that we might do here as an example might be, we might be interested in the internal energy. The internal energy that that people will typically use is they'll typically write this as a capital U. And they'll use a lowercase u this way. And similarly, we might be interested in, say, the entropy which we would write as the capital S. Now this should have been a U, and a lowercase variable there. So we're going to use this notation as we go on, and we're going to think about conserving these different quantities. And so we're frequently going to see the product of things that look like this, that we can recognize here, where the intensive quantity here is the velocity, or another way of thinking about it is the momentum per unit mass, multiplied by the mass per unit volume, and then integrated over the volume. And using these ideas, we're now going to try and develop some equations that allow us to take an arbitrary volume and write down some conservation equations for it.